Now we're going to talk about valence bond theory. So the Lewis model is an oversimplification, but it's still very useful. The more advanced bonding theories involve quantum mechanics, and there's a lot of math, a lot of really kind of crazy math. And so we're not going to look at these in a quantitative way. We're going to look at them in a qualitative manner. And so that's what we're going to do with valence bond theory. So electrons are found in quantum mechanical orbitals that are localized on individual atoms. And we've talked about these, the S, P, D, and F atomic orbitals. So what's new here in the valence bond theory, let me make sure I didn't skip anything. What's different here is that we can hybridize these atomic orbitals. So kind of mash them together, change them a little bit. So when two atoms approach each other, the electrons and nucleus of the one atom interact with those of the other atom. And valence bond theory is going to look at the change in energy resulting from those interactions. And if the energy of the system is lowered, then a chemical bond will form. So here we are looking at two hydrogen atoms approaching each other. So this is the distance between them. So large distance here, and here they would be like on top of each other. And energy is increasing as we go up. So as we're bringing these atoms closer together, the energy is going down because they're forming a bond, essentially. And it's going to go down and down and down until it gets to this point. And then if we push them any closer together, the energy is going to start to go up. You're like, no, that's too close, right? It's like, you like to be near people when you're talking to them, but you don't want to be a close talker, right? If somebody's like stands too close to you and talks, it's not good. So there's this sweet spot here. Well, this distance turns out to be the bond length, and this energy is the bond energy. It's the distance at which the system is most stable. And so what we're looking at is the overlap of the s orbitals of the hydrogen atoms. So as they overlap, they're going to get attraction. If they get too close, there's going to be repulsion because of the nuclei. So that interaction energy is usually negative. It's stabilizing. If those orbitals that interact have a total of 2 electrons that can spin pair. So in our atomic orbitals, as we were putting electrons in, one would be an arrow up and one would be an arrow down, right? Because that kind of helps to explain how can you have 2 negative electrons in this same place, right? Well, they're spin paired. And so when we form this bond by overlapping orbitals, it's going to work the best if we have 2 electrons and they can spin pair. So one will be positive, one will be negative. Usually the electrons come from 2 half-filled orbitals, meaning each atom brings 1 electron to share, and then they share and that makes the bond. But you can also have a situation where both electrons come from the same atom and the other atom is bringing an empty orbital. This is more like a charity situation, right? You don't have any, I'm all good, I'm going to share with you. This is called a coordinate covalent bond. But we're going to talk about half-filled orbitals. So we've got 2 atoms that have half-filled orbitals. As they approach, those orbitals will overlap and the electrons will take on opposite spins. So an electron has a spin, but its spin can change, right? So the summary here is we've got valence electrons of the atoms in a molecule reside in quantum mechanical orbitals. The chemical bond results from the overlap of two half-filled orbitals with spin pairing of the two valence electrons, and the geometry of the overlapping orbitals determines the shape of the molecule. I'm not sure how much of that made any sense, but do you have any questions yet? So this is kind of what we're talking about. So here we're looking at a sulfur atom and two hydrogen atoms. So the hydrogen atoms each have one valence electron, one electron total, and that one electron is in the 1s orbital. Here's sulfur's valence electrons. The 3s orbital is full, and there are 4 electrons in the 3p sublevel. So 1 is full and 2 are half filled. And so what we're looking at here is, what if this orbital overlaps with this orbital? So that's what we're showing right here. This is a p orbital, 1 electron from the sulfur, and the s orbital, hydrogen has 1, and in that overlap we have a pair of electrons. Here's another hydrogen, it has an electron, and it's going to come up to this other half-filled orbital. They're going to overlap and have a pair of electrons in that overlap. Does that make some sense? Okay. So there's an issue with this, though. So the actual bond angle is 92 degrees. Valence bond theory at this point is predicting 90 degrees, right? Because these are p orbitals, and they are perpendicular to each other. So this bond angle here we would expect to be 90 degrees, but it's actually 92. And if we look at Vesper theory is going to predict that it's less than 109.5, but definitely not 90, right? So there's something that's not quite right. These are pretty close, but still not really very great. So the answer to the question, what is a chemical bond, will depend on the bonding model that you're thinking about. So according to valence bond theory, what makes a chemical bond? A lone electron pair, the overlap between half-filled atomic orbitals on 2 atoms, the overlap between filled atomic orbitals on 2 atoms, or a shared electron pair between 2 atoms. It'll be B. Letter D is how the Lewis model views bonding, a shared pair of electrons. So here we're looking at the overlap of 2 half-filled orbitals. So if we look at carbon and hydrogen, so here again is hydrogen's orbital diagram, and here's carbon's valence orbital diagram. This is supposed to be another section.